Welcome to our 7th video lecture. What we're going to do is get down to a really basic type of calculation that mechanical engineers are responsible for, and that is for sizing a system that can take a fluid from one point to another. So, starting with the most basic type of example, horizontal flow. So I got some water over here and we want to get it over to this tank over here like this. We're going to go with some piping. We're going to go with 1-inch inner diameter pipe, and we got to take it 100 feet. So if these two water levels are the same, which is what I intend, there's no way that the water is naturally going to flow. And we need to actually get a pump. So this represents a pump that's going to take it over. And by the end of this course, you have a pretty good idea how to do that. And that ends up, this type of work ends up being bread and butter for a lot of engineers. All right, so how to go about analyzing this? In short, you need to figure out the pressure drop for this 100 feet of pipe. That's the bottom line. But a few more details on it to get an idea what's going on. So bear with me for just a second. This is actually what we're responsible for this situation. First of all, what we want to do is we want to decide the nature of the flow. And these are our three main choices: inviscid, laminar, or turbulent. Okay. In addition, we want to be able to get a pressure loss calculation in two different ways, in terms of velocity pressure, in terms of head. Okay. I'm missing one thing on the list of what's important for this. Another thing we want to do is we want to decide for our flow at some point, like this entrance, is it fully developed, or are we still in the entrance region where the flow regime is developing? Okay, once we have that kind of stuff worked out, to get the pressure drop, we're going to need something called the friction factor, and that takes a little bit of work to understand. Once we have the friction factor, we can put it all together. So this is a rough outline of what we're going to try to work through today, and let's go ahead and get going. So the first thing that you're going to do if you do some work like this is decide the nature of the flow in the fully developed region, and that involves doing the Reynolds number. So let me get it up there and then get you guys going. So we're going to do it twice. All right, so your first thing to do is Reynolds number calculation. Let's say we have half a GPM going through there. Is that going to be laminar or turbulent? And what I'd like you to do is stop the video and go ahead and do that calculation. You don't want to be the type of entry-level engineer where your supervisor gives you this calculation and you say, I don't know what to do. If that's the case, you should say you don't want to do, but if you do say that, then you're going to get comments behind your back like, whoa, this person must have been absent the day they taught engineering in engineering school. So try not to just punt on this one. Get going, look up your Reynolds number formula and see if you can take this value and convert it to a Reynolds number. All right, let's see how you let's see how you did. I got laminar flow. So taking a look through the calculation, there's our one of our two basic Reynolds numbers formulas. Either one should work. Either one should get you this correct value. This one is the more classic one. I personally like the M.1 one better. It's all good though. So we need the average speed, and average speed is volume flow rate divided by area. This volume flow rate is in gallons per minute. And since to do this Reynolds number, we want the speed in feet per second. You've got to convert this gallons per minute to cubic feet per second, and there's the calculation. We've gone over the conversions for that. Area should be in feet squared, so 1 inch diameter that is a 1/12 of a foot diameter, and so you do the calculations, I get 0.204 feet per second. So if we have 0.5 GPM, this water is moving this water up here is moving very slowly, and then we go through our Reynolds number calculation. I didn't show the units. Right now, you still might want to do that verification, and I get 1,411, so we got laminar flow. All right. If you were an engineer and doing this work, you might say, hey, could we save some money? This actually is 1 inch diameter copper pipe. We're going to do galvanized iron for our example, but this little length of pipe I got right here, it's expensive, okay? And so if I'm going to use 1-inch pipe to transport a half GPM, I'm looking at for quite a bit of an expense. So two things we might think about. Could we make that pipe smaller and still be okay, where okay has not really been defined? Or could we put more flow in? So our other alternative that we're going to take through class today is to say, look, let's push things. Let's have a lot more flow in this case. So what we're going to go with is 10.65 GPM. Okay, 10.65 GPM. Go. See if you can crank through and get that Reynolds number in less than 2 minutes, particularly if you're smart about looking at part A and using your results there. All right, I'm back. I got turbulent flow when I went through and did this. I got a Reynolds number in the order of 30,000. So right or wrong, regardless, what is the kind of slick way to do this? So we still have the same relationship, and you can see that every single term in this relationship, if it's still 60-degree water, still 1-inch inner diameter pipe, is going to be the same. The one thing that's going to change is our average velocity, okay? Velocity is volume flow rate over area. Area has stayed the same, but volume flow rate has just upped to 10.65 GPM. So you essentially can redo this calculation above, where you take the speed and replace it with a new speed based on a larger volume. So basically what I did was I took my earlier speed, 0.204 feet per second. That was based on 0.5 GPM, and now I have 10.65 GPM. So I took this number and divided it by 0.5 to get rid of the 0.5 and multiplied it by 10.65 to replace it with 10.65. And I got, hey, that water is moving a lot faster, 4.34 feet per second. And as a consequence, the Reynolds number I get is 30,020. All right. Hey, if you couldn't see how to do that quickly yourself, no problem. This is the bottom line, that we want you to be able to do this calculation successfully and fairly organized, reasonable time calculation. And of course, we would like you to work towards being able to think this way and get that worked out faster. All right, the next step is non-calculation step. It is helpful to be able to visualize what's going on with particle motion. So I got 3 cases up here: laminar, turbulent, and viscid. There should be a 4th case, which would be transitional. But we're going to stick with these 3 this semester, and that's a really, really good start to understanding what's going on. Okay, so this dot represents some particle of fluid that's in that pipe. Dotted line is the center line. Okay, let's start with this particle like that. Maybe test yourself. What is that particle's motion going to look like? Well, the answer is the same for all 3 cases. No slip condition. It is just going to stick there on the wall. So we have 0 velocity at that point there like that. Okay, let's go to the center line. Well, if it's laminar, okay, that means the layered flow. So we can envision these layers of fluid sliding along to the right, one on top of the other. And the one that's going fastest, if you remember from laminar flow, is this middle one. So this middle one is just moving to the right like that at a certain speed. Its speed for laminar flow is twice the average speed. Okay, what about this particle up here like this? Okay, it's going to be moving to the right, purely to the right, but with a little bit less speed. Okay, so that's laminar flow. Layered flow, smooth flow. In the case of a horizontal pipe, purely in the x direction. All right, next thing, what if it's turbulent flow? Okay, what if it's turbulent flow? Transitional flow, by the way, would be in between laminar and turbulent. Well, turbulent flow, the particle is still, this particle right here is still stationary. This particle is moving to the right, okay? This particle is moving to the right overall, but at times there are little perturbations or little swirls associated with it. So what we have is general flow to the right, but we have some vertical motion as well. For laminar flow, we speak of there being a U, okay, horizontal velocity. Here, we speak of there being an average U. It's going to speed up and slow down as some of its motion goes vertical, but there is an overall average U. Okay, by the way, this one's average U is going to be 0 for turbulent flow, and then it's the actual relationship of this one's path to this one's path. We'll get to into a minute. All right, inviscid flow. See if you can do the 3 dots for inviscid flow. I'll give you just a second. So I'm going to do this bottom dot, pipe wall, this dot right here, center line, this dot right here, maybe halfway between the center line and the top of the pipe. Okay, inviscid means there's no viscosity effects. We're going to visualize maybe this one as not slipping, but the rest of them just end up moving to the right. This little particle right here is not slowed down by that particle there like that because there is no viscosity. There are no inter-particle cohesive forces. So this one here would be moving to the right, maybe at a certain speed, and this one here would be moving to the right at the same speed. We've got no viscosity. All right, so there is our first visualization. What are particles doing? All right, second visualization that is useful is to think, okay, what does the velocity profile look like? Could we come up with a graph u at y that shows the velocity at every single point? Well, again, for all these work that I'm doing, you're welcome to shut off the video. I'm just going to keep going and get the laminar u at y profile. So y is often termed distance from the center line. So this would be a negative y here. This would be a positive y. Taking this particular point right here, and I got that dash line right there over there. Okay, what's it going to look like? Zero velocity at the pipe wall, maximum velocity at the center line, and parabolic velocity profile, which often is, you can draw the parabola, but the more clear thing is to do some arrows indicating slow, faster, fastest, and then exactly symmetrical. Okay, so there's a poor but along the right track drawing of the laminar velocity profile. You, in our previous lecture, and we gave you equations for that profile. Homework 8, you work with the equation for that profile, and you are responsible for actually knowing it. Okay, turbulent. What's this going to look like if it's turbulent? Well, go ahead and get the top and bottom dot. Okay. Well, first of all, you might think that's going to be a real mess to try to graph what's going on turbulent because every particle is moving up and down. But what we're doing is doing the average u velocity. So basically, on average, every particle is moving in the u direction. All right, here's what I want you to know, and maybe a way of thinking about it. In turbulent, we're going so fast that some of the viscous effects are overcome. Not so much at the wall. So this one right here, it's going to be slower because of the viscous effect of the wall. And here it's going to be slower because of the viscous effect of that wall. It's going fast enough that those viscous effects don't penetrate very far. And so you get some middle area where it's just going really fast like that, and almost uniform flow, almost uniform flow. And so you get a velocity profile. I'm not drawing it very well. I probably shouldn't have put those arrows so much to the right. I will, for homework number 9, give you the key figures to look at, but you get a velocity profile where it increases and then it is virtually flat in the middle and goes down like that. So there is a velocity profile for turbulent flow. And again, ideally, I would make you responsible for the equation for that. I will refer you to the equation, but I just want you to know this shape. All right, 1 to go. Go ahead and get the velocity profile for inviscid flow. Yep, that's it. We can think of there being a no-slip condition at the wall, but there's no viscosity essentially, so there's no effect. So we end up just having a uniform profile like that. And it's kind of interesting to think about. Is the turbulent profile closer to the laminar or closer to the inviscid? And the turbulent profile is closer to the inviscid. There are viscous effects at the wall, but in the middle, it kind of gets free from viscosity, and we end up having something like a uniform profile. All right, the last preliminary thing to do before getting going on that fundamental calculation, which is, hey, how much friction are we talking about for our piping system, is to get the entrance length. So we've got some fluid entering a piping system, and eventually it's going to settle into one of the 3-4 flow regimes: laminar, transitional, turbulent, or maybe inviscid if we can make if that's a reasonable assumption. So, but it doesn't actually, if you think about laminar flow, if this flow ends up entering at a uniform velocity, say like 0.2 feet per second, 0.2 feet per second, 0.2 feet per second, that middle's got to speed up, and the portions that are close to the pipe edge have to slow down because of viscosity. That doesn't happen instantaneously. Your car doesn't go from 0 to 50 miles per hour instantaneously. There's a transitional length or a transitional period. So what distance is that transitional period? Well, it turns out that people have been able to analytically work it out for laminar, and then as always for turbulent, it's an empirical formula. So go ahead and write this formula. This is our first formula for the day. LE stands for the entrance length. How far do we go before we hit fully developed flow and our relationships for fully developed flow, like the velocity profile, actually hold? And so that's the entrance length. It turns out the relationships are nicely worked out in terms of the pipe diameter, so LE over D. Here is the formula for laminar flow, and here is the expression for turbulent flow. I don't have one up there for transitional. If you go on in fluids, that'd be a great thing to work on. But for time being, let's go ahead and work with that. So easy enough. Let's just go ahead and see if you can give it a stab yourself and come up with how far this entrance length is in feet if it's laminar. I'm going to work this one out step by step and show you the reasoning. It's really not that complicated, but here we go. First of all, we have to know the Reynolds number for our situation. So once again, it's the previous situation, 0.5 GPM, 1 inch inner diameter pipe, 100-foot length total. What is the entrance length? Okay, well, the first thing to do is it involves the Reynolds number, so I should write that down. For our first case, for our laminar case, we had 0.5 GPM, and our Reynolds number turned out to be 1,411 approximately. I forget what I wrote down earlier, but it's something like that. Okay, so basically what we're going to do is we could plug and chug, all right? Or maybe we could do it all in one step. The entrance length is going to be equal to 0.06 times my Reynolds number, 1,411. And then I need to multiply it by my pipe diameter. And this is the inner diameter of the pipe. Well, it was 1 inch, so I could multiply it by 1, but I would like it to be in feet, so I would divide that by 12. Okay, let's see if the units work out. This is feet, Reynolds number, unitless, 0.06 unitless, so that's going to turn out to be feet. And then we'll just plug and chug, and I'll see if I match up what you guys got out there. Okay, and I got an entrance length of about 7 feet. 7 feet and just a little bit, 7.06 feet. All right. So one thing that you'll eventually do is say, hey, can I ignore the entrance length? Is it a small portion of my total pipe length? Total pipe length with 7 feet, 100 feet, we probably wouldn't ignore that if we're going to try to be precise. Okay, I encourage you then to go ahead and do the next two. Get the entrance length if it is turbulent, and the entrance length if it is inviscid. All right, so first my answers and then the work. So I got an entrance length of 2 feet, for approximately 2 feet for turbulent, and for inviscid, I got an entrance length of 0 feet. Okay, so let's go through the work. All right. Sorry, I'm being a little bit consistent. I worked out these problems a couple different places. That may look like a big deal if your Reynolds number is slightly different than that, but these last couple digits for turbulent flow a lot of times don't make a difference. So if you're close to that, I might be wrong, you might be slightly off based on rounding, but it's good enough. Okay, I did it a slightly different way. I just plugged into the formula and did LE over D, and I got 24.5. And then I did the math and solved for LE, and I got 2 feet, about 2 feet. All right, so first of all, the difference, 7 feet versus 2 feet. Okay, well, if you think about what's going on, this fluid is going so fast that it almost essentially comes over a lot of viscous effects. That is a very rough statement, but it's appropriate in this case to think of things that way. Well, it turns out it settles into the turbulent flow fairly quickly. This one, the laminar case is much slower, and so there's a gradual approach to fully developed flow, and it's 7 feet. Okay, what about the inviscid case? 0 entrance length. Well, the idea there are essentially no viscous effects, so the flow just ends up entering the pipe and is as it is outside the pipe. So we have 0 entrance length. So, hey, just a note on the previous calculation. As far as the entrance length goes, for a lot of the work that I've done professionally, which would correspond to a lot of the work that many mechanical engineers do, have been able to get by without looking at the entrance length that much. And if you take a look at the turbulent flow calculation, that might make some sense. We said that water oftentimes is turbulent. It has a really high density, and so for most flows, it ends up turbulent. And in the turbulent case, the entrance length is not that long. But if any of you guys end up going into, say, any of y'all go into car manufacturing where you're working with engine oil, it's much more likely it's going to be laminar. And there are cases where we want flow to be laminar. So turbulent entrance length calculations can be important. All I want you to be able to do is do the entrance length calculation, and we won't think about delta P for the entrance length. We're going to get down to delta P once flow is fully developed. So our equations for now are going to be fully developed. So there are many different ways to go ahead and calculate pressure loss for pipe flow. But what has emerged is just the general idea, hey, if the fluid's moving fast, where I put this in quotes, what's the delta P going to be like? And the bottom line is that we end up getting a large delta P. All right, and that is a thought process that goes back through people's minds as we go through it. So how are we going to quantify fast? Well, it's usually calculated in terms of energy term. It's thought of as one of the energy terms in the Bernoulli relationship. So the Bernoulli relationship, all three of these are basically Bernoulli type expressions, where what they're doing is doing the total mechanical energy of a fluid. The pressure energy, the speed energy, and the elevation energy. And so if we're going to think about this fluid speed in terms of its pressure, there's our key term right there, rho v squared over 2. Turns out we could also do it in terms of feet squared per second squared, and there would be our term right there like that. And finally, we can do it in terms of feet. The energy of a fluid can be expressed in feet, and if we're doing that way, there's our expression on that. More about that later. We're going to start out with this being a quantification of basically how fast, or better put, how much kinetic energy a fluid has. So our delta P equation is going to have that term to the right, and let me get that in there for you. Okay. And by the way, this equation we got up on the board, on the whiteboard at the end of last lecture. So hopefully that you can say, oh, this looks familiar. Okay, what else would contribute to delta? What other things should we consider if we're doing delta P for a fluid from this point to that point right there? Well, the longer this pipe is, the more pressure there's going to be, because it's just going to keep losing pressure because of friction the further it goes. So there ends up being an L over this here, right? In this case, like there. And then it turns out that for a certain flow, the bigger the diameter is, the less the fluid has to squeeze in there. So you can think about the reason why diameter is in the bottom of that expression. All right. And people who worked on this said, hey, we can think about it this way if we add in some sort of friction factor for the flow. And that is our bottom line equation for this stuff, okay? Is that we are going to figure out the pressure loss within a pipe by doing a kinetic energy calculation, a length divided by diameter, and we're going to find some sort of friction factor. So before we do that, though, I'd like to get the alternative equation up there. Okay, the alternative equation is that if we go from rho v squared here to v squared over 2g. So what that means then actually is we would take, if we were to do that manipulation, we would divide out the rho, okay, and we put a g in there. And this, instead of being a pressure in PSI, would be a loss in units of feet, or if we're in SI units, it's units of meters. So let me get the alternative equation up there. Bear with me for just a second. This is another very, very common way of doing it. If we want to get the friction loss, which is sometimes called the head loss, okay, due to a pipe, and that's called a major loss, which is opposed to a loss from, say, like an elbow or an expansion or a contraction or a valve or something like that else that's in our piping system. We're going to again do that energy term, V squared over 2G. We're going to have L over D, and we'll have F. And that's going to get us pipe loss in feet if we're in English units, and SI, and meters if we're in SI units. All right, so let's get oriented on that calculation. So here's our first example that may look very intimidating, but copy it down, take a deep breath. It is what we started with. So let's say we got some 60-degree Fahrenheit water. We want to move it at 0.5 GPM through a 1-inch pipe, inner diameter. We're going to move it 100 feet. And we actually, for this pipe, know that the friction factor is 0.5. I'm making that number up, but we're just going to work it out to use that number. Hey, what is the pressure loss going to be? And I'd like you to get it in PSI, because that's a pretty standard way of working that out. Okay, I will work through it step by step, but give it a shot and see if you can figure it out yourself. First of all, that'll build your confidence. Secondly, that'll allow you to fast forward through the video and get done sooner. All right, well, here's some of the work. There's our formula that we're trying to fill into. A lot of the stuff we have, but the speed is not given in the problem. But hey, we did that earlier. Hang on for just 1 second. Let me make. Hey, sorry about that, you guys. Actually, I had the wrong speed. So for 0.5 GPM, when we had that earlier, we got a pretty slow speed, 0.204 feet per second. So I've gone ahead and just filled in all the numbers where the 1.94 is the density of water. I haven't done my unit check, so I'm going to do that down below. Is thinking going across here, this is a length in feet, and this is a diameter in feet, so those cancel out. And we end up just having to do this stuff over here, at least for starters. Slug for foot cubed, foot squared per second squared, okay? We're hoping for a slug foot per second squared to get pounds because we want PSI. So basically I could take one of these feet and combine it with the second squared and with a slug, and I get a pound there. And I'm left with another foot there that cancels out with a foot cubed there, and I'm I've got a pound per foot squared. Okay, that's what I got so far. What about this 0.5? Well, this 0.5 is a unitless friction factor, so we are done. And let's see if, I hope my numbers match you guys, but on my calculator, I got 29.1 for that. Wow, that is a really, really large number, but that is pound per foot squared. By the way, it turns out that that is an unreasonable loss in this situation for laminar flow, and the culprit is this estimate that I gave you, which is 0.5. It turns out our friction factors in general are going to be smaller this semester. All right, so to convert it into PSI, I would divide it by 144. Okay, and I get 0.2 PSI pressure drop. That is non-trivial, okay? But at the same time, it is something we would need to take into account for if we were doing some pumping, trying to get that water to 100 feet. All right, good. All right, so back to what we need to do to finish off and actually make you be able to use this formula correctly. But once again, very important problem in engineering to figure out the pressure loss of a fluid as it goes from one point to another point. Turns out it has been very productive to think about it as coming from an energy term, how much energy of motion does the fluid actually have, and proportional to the length, the longer the pipe is, the greater the pressure drop, inversely proportional to the diameter. Engineers wanted to think about it that way. This formula kind of didn't uniformly work out if you put some general number up there. So they came up with something called the friction factor, which is determined from the situation. So you need to gather some information in order to turn out the friction factor. And let's get started on what kind of information we're talking about. Okay, so there's a couple different ways to get the friction factor, but the main way we do it is go to table B1. So maybe while I'm chatting for just a second, I encourage you to get table B1. It is conveniently located in the back of your book. Maybe pause the video and try to get that. And I'll start talking about it right now. Okay, so there is our Moody chart. Let me see if I can move this out of the way so that you guys can see what's going on. Okay, so getting orient on it, I think it's going to go better for you if you combine looking at your own Moody chart and also taking a look at the screen. So what we're going to do is we're going to pull the friction factors for any scenario. Well, not any scenario, but most scenarios, we're going to pull them from this left side. So our job, if we're sizing pipe or pumps, et cetera, figuring out what's going on, is to get an F value there. And you can see that in general, they're quite low. All right, how do you go about figuring out what value to use? You have an x-axis value, a y-axis value, and in general, but not always, that allows you to get to a curve and a point on a curve and then work out the friction factor. Hey, let's get the x-axis value. Let's say the x-axis, I don't have it on there. The x-axis is the Reynolds number. So let's say the Reynolds number is 20,000, turbulent flow. Let's take a look at that. So we're going to go down to the x-axis. There's 2 times 10 to the fourth. So that's 2,000, okay? Over here, we've got 20,000. Over here, we got 2 times 10 to the third, which is 2,000. So over here, we're kind of in the laminar range over here like that. And then we get over here and we're the turbulent range. So this is 2,000, pardon me, 20,000 over here like that. So if we know for our flow, our Reynolds number is 20,000, we're somewhere on this axis here like this. Okay, the second value that we have is how rough the pipe is. And I'm going to talk about that in just a minute, but that is called the relative roughness. And it's a ratio of the roughness to the pipe to the inner diameter. And what we can do then is do a calculation. So let's just say that we turn out our relative roughness is 0.004. Okay, that means then that we are on a certain relative roughness curve. So really we got 2 things we're going to do. We're going to identify a vertical line that we're on for turbulent flow based on the Reynolds number. Okay, then we're going to identify a curve, and we would get the intersection of the curve and the Reynolds number line. So basically in this case, what I would do if I had my relative roughness was 0.004 and I wanted to get over to the 20,000 line, I keep following. Notice that my 0.0004 curve turns up, okay, and I am intersecting the vertical 2 times 10 to the fourth line right about there. And then what I can do is take that intersection point, okay, and then I go to the left and read my friction factor from there. So again, 3-step process. First of all, identify your Reynolds number, particularly if it's Reynolds number. Secondly, get your relative roughness curve if it's turbulent. Third, find the intersection of the vertical Reynolds number line and the roughness curve. You might want to take your pencil and put a dot on that point. And then once you have that point, go from that point over to the left to get the friction factor. All right, I'm going to work through an example with you guys related to what we did earlier, but before we do that, we should talk about roughness and relative roughness first to make sure we're clear on that. All right, pipe roughness. So, ordinarily you think of a pipe as being nice and smooth on the interior, and copper pipe is pretty good, but if you look closely at it, you might see some things that contribute to some roughness. And obviously roughness is going to contribute to friction, just as in your normal dynamics. In dynamics, we measured friction with a coefficient of friction. Relative roughness is similar to that. But to give you an idea, if you took some sort of pipe and you really got close to it, you would see little bumps going up and down there like that. And there would be some sort of length of that bump, okay? And the book uses this symbol for that. What is the average length of that roughness or that bump? And of course it's an estimate, but it's well documented for different types of pipe, all right? Hey, what difference does it make? Well, for turbulent flow, it makes a huge difference, because you remember, if you have any sort of bit of pipe, any any sort of bit of fluid, it ends up having a variation in its flow up and down, and that can include down, probably there shouldn't be any backwards basically, but down basically into that rough area and up. And so any fluid, any particle of fluid that's not following the no-slip condition is actually going to penetrate in that area like that, and we're going to end up getting some frictional effects according to it. All right, so for your Moody chart, table 8.1 in the book, nicely has some common pipe roughnesses. We can always look them up for any particular pipe. We're going to do galvanized iron, and so 0.0005. All right, if you think back to the Moody chart, though, if you look at your Moody chart, the column on the right side, okay, which we use to get those curves, in the Moody chart, this is not roughness, okay? This is relative roughness. So basically, what we're trying to do with relative roughness is say, hey, how big a difference does this make? Well, if this roughness length was like an inch, which would be ridiculous, but it'd be really large, and we're talking a 3-inch diameter pipe, the roughness section is a huge portion of that whole pipe. On the other hand, if the roughness was 0.2 micrometers, and that would be fantastic pipe where it was really, really smooth, okay, and the pipe was a 4-meter diameter pipe, well, that little rough section is hardly anything, and it is not going to be that significant. So what is traditionally done is we take, to do our relative roughness, we take E divided by D. And you might want to write that down as another formula from today, okay? Excuse my abbreviations. I'm just trying to be concise and get you guys going. Eta over D is pipe relative roughness. Okay, we want it to be unitless, okay? We want it to be unitless. So what we're going to have to do is take this 0.005 feet and calculate the relative roughness and do a conversion. Okay, I encourage you to pause the video and see if you can get the relative roughness for our example where the diameter is 1-inch pipe. All right, that one turned out nice and easy. Roughness divided by pipe diameter, 0.0005 feet, and the diameter is 1/12 of a foot. So I got a relative roughness of 0.006. And that's nice and convenient because that is one of the curves on the Moody chart. And so let's go ahead and get going. Let's, for example, I'll get it back up there, even though you guys get going. Our first example, okay, was we did 0.5 GPM, okay, and everything else is the same, okay, but we're going to add in addition that we're going at with galvanized iron pipe, okay. And what is our delta P? Okay, so I encourage you to pause the video and get out a sheet of paper and make that your example. Recall that this is a 1-inch diameter pipe and it is 100 feet long. What kind of pressure drop are we talking? And you certainly could do it in a variety of units, but let's get it in PSI. All right, definitely gave you a challenge with this first bit. So basically what, again, we were doing, which we're taking our water and pumping it from here over to here, 100 feet, and we want to figure out the pressure drop, and that will say help us size the pump or think how this is going to work out. So our first case in almost all pipe flow situations is to calculate the Reynolds number. We got that earlier where we got somewhere around 1,410, so it's lambda. Okay, so I'm looking across here and I'm going to try to get each of these terms. I know how to do this term here. I know how to do the flow energy term. I know how to do L over D. But what about the friction factor? So, hey, I'm following what the professor says and I'm getting a little frustrated, understandable. We'll try to straighten you out. I did eta over D and I got 0.006 earlier. So now I'm going to go to the Moody chart. Let's see, getting us to the Moody chart. Hopefully you're just looking at your own Moody chart. In any case, all right. So we talked about going over to this roughness and getting that value. So we're on this 0.006 curve. That's one thing we need to do. Second thing, following my instructions earlier, is we need to get the Reynolds number, vertical line. There's 2,000, we're laminar. We're somewhere in here like this. Okay. the thing to understand, if I follow this 0.0006 line over, horizontal, curving up, curving up, curving up, curving up, it doesn't make it all the way back. So what's going on with that? Well, this idea, this portion of the Moody chart essentially is for turbulent flow. The roughness matters for turbulent flow. If we're in laminar flow, there's two ways to think about it. One, we can use this line and we can certainly come up with the values from that line. We can skip the roughness and just use this curve here to get the intersection of our 1,400 vertical line, this curve, and go over here like this. Okay, but I want to give you another way of thinking about it that for many of you will be easier. So let's go ahead and take a look at that. So the idea that I'm going to want to try to get across is that if it's laminar flow, this roughness doesn't matter. And a good way of thinking about it is, remember, there's a no-slip layer. Okay, that no-slip layer is down at the pipe walls. And hey, you can think of that no-slip layer as essentially making a smooth surface, because that fluid is just there filling in those little ups and downs, and it stays there. It stays there. Okay, this fluid up here, does it ever make a turn and actually go in and contact with that wall? No, it's not. It's laminar. Turbulent flow, on the other hand, I mean, turbulent is swirling flow that has quite a bit of effect. So we could get a swirl where it actually goes in there and actually ends up contacting that pipe surface. But in this, if it's laminar flow, that roughness doesn't matter at all. So it turns out if there's laminar flow, there is another alternative. And that is that you can just use the Reynolds number to get the friction factor. And that is the next equation to write down. It essentially is virtually our last equation of today. To get the friction factor, you can do 64 divided by the Reynolds number. All right, so taking a look at it again, there's the friction factor I got by doing 64 divided by RE. Here's my governing equation. So I've gone ahead and filled in the numbers. L over D is 1,200 unitless. Rho V squared over 2 is 0.0404. And if I crank through that on my calculator, by the way, a little bit rounding here, so my numbers might turn out slightly differently than yours. 0.0454. Sorry about that. Hang on. Okay, I get a pressure drop of about 2.2. Non-trivial, but we got to note that that is in pound per feet squared. So to convert it in PSI, I'm going to divide by 144, okay, and I get a pressure drop of 0.015 PSI. Wow, that is one low pressure drop. But that might make you think, hey, if we go back to the original situation, hey, let's just skip the pump. We got to pressurize this water by less than a PSI to get it across there like that. Maybe there's some other way we can do it. But once again, this stuff right here is called the major losses or the pipe loss. It ignores losses associated with fittings, like fittings going into the pump and fittings come out of the pump. Entrance length, I really haven't addressed. There is more to it. And that's all in chapter 8. It's pretty interesting stuff. But let's go ahead and do the other example and get the contrast. So see if I can describe it to you verbally. Same flow, same situation, 1-inch pipe, galvanized iron. Okay, but now we've got a flow of 10.65 GPM. What is the pressure drop? Go. All right, so some of the work, again, there's our situation. We're trying to pump water or get water to move from one place to the next. 10.65 GPM, 1-inch pipe, governing relationship. Now, that's pretty rough, but as far as reading the Moody chart, that's not bad. So the two bits of information we need to read the Moody chart are the Reynolds number and the relative roughness. So first of all, you get your Reynolds number line. All right, and you're welcome for test 2 and for test 3 to, print out a copy of figure B20 and mark it up as you're working. I encourage you to do that. A lot of times I have a ruler with me and I end up laying down the ruler on the chart to get my point. So there's the 3 times 10 to the 4th vertical line. So we're somewhere on the vertical line. This is the 0.006 roughness line, and I can follow that roughness line, and I'm looking for the intersection. So there's some good work there. I've identified my roughness line, I've identified my friction, my Reynolds number, and now I need to get my friction factor, and I just read horizontally across and get the value here on that axis. All right, how precise do you need to be? Well, at first you're gonna feel like, yeah, this is really tough. But if you take a little bit of time and go through and reading that, you're gonna get good at that. For starters, I know it's somewhere between 0.03 and 0.04. I want you to get which one it's closer to. It turns out in this case, it is pretty much right in the middle, okay? But a good, if you said 0.035, hey, that's pretty good. It turns out it's just a little bit below the 0.5 line. So I got a little bit, my estimate is that. Please don't stress about that too much. Start by recognizing it's between 0.03 and 0.04 and somewhere in between. Okay, hey, now we've got everything that we need to do. How is this pressure drop going to turn out? The previous example, we got hardly any pressure drop at all. Well, why don't you go ahead and go through the calculation quickly yourself, and I'll get the numbers up there. All right, I got 5.3 PSI. Let's see how that matches up or how that worked out. So I've got my friction factor, and then there's the governing relationship filled in. L over D is still 1,200 unitless. And then rho v squared over 2 is much larger now because we have a lot bigger speed. I believe it was like 4.3-ish, 34-35 feet per second. So I crank through that. Got to remember that this number here is pound per feet squared. So when I do that, I get a very large number, but then I divided it by 144 to make it from pound per foot squared to PSI. And that turned out to be about 5.31 PSI. Okay. You're almost done. You're about ready to get yourself hired out, because in a situation like this, even though this is very simple, someone might say, look, we want to get the water pumped from here to here. We don't have that much money for piping, so we're going to go with smaller piping, and we're going to try to squeeze 10.65 GPM through that 1-inch pipe. Hey, engineer, what size pump is it going to take? Well, if you can, to a manufacturer, if you can specify the GPM and you can specify the friction, they will pick out a pump that will do that for you. And hopefully we'll have a little bit of time to talk about that later on. But I know that Professor Marbaugh in ME120 gets you working with pumps and figures out what's going on with that. And of course, in the HVAC class we teach here at Sac State, we go over more details on that. So we actually are pretty close to getting it. We tell them 5.31 PSI. They're going to pick out a pump. But there's one more problem actually, is that there's several, but the main one is this, is that the manufacturer likes the pump pressure or the pressure requirement to be specified in that alternative measurement, which is feet. So let's talk about that to finish things off. All right, so quick summary, reminder with one additional detail. If we want to figure out the pressure drop in units of pressure, there's our formula. Just got to be careful with units. If we want to figure out the pressure drop in terms of feet of a water, say feet of H2O, well, one way we can get it is just get rid of the rho and divide by G. And so there's my equivalent relationship. But it's also helpful to remind ourselves, hey, how do we go from this formula right here to the H formula right there? Or the other way around, if we have to go the other way around. Well, basically, you're going to take the delta P to get H, you could take the delta P formula and divide it by rho G for the fluid that you are working with. That's sometimes called the specific weight. And this is a useful way to go, and that's what we're going to do down below. Just a reminder, though, a lot of times our specific weight is in pounds per foot cubed. So we would like this delta P to be pound in feet squared when we do that manipulation. Okay, so to finish off class, let's see if we can get this chart filled out, okay? We're gonna do the 2 different cases, okay? So case 1 was where we had nice, simple laminar flow, all right? And we ended up getting in that 1-inch pipe, and we got a pressure drop of, in PSI, 0.015 PSI. So what I want you to do is I want you to convert that to head, feet of H2O. And then I'd like you to get the pressure drop for turbulent. We just did that a couple minutes ago, and do the same thing. And of course, let's get the inviscid value. So 5 values to go. See how many you can get on your own. All right, so here's 2 out of 3. By the way, you may get an email from me. I want to check this number and make sure that it's right. It looks like our calculations are correct, but that is a very low pressure drop. Okay, but anyway, to convert it into feet H2O, I'm going to take this PSI and make it into pound per foot squared. That means multiplying by 144. And then I'm going to divide by the density of water, which is 1.94, and the gravitational constant, which is 32.2. And I get hardly any feet, equivalent feet of pressure drop. So this much water has a column of water this high has the pressure equivalent to that. Okay, 3 to go. This one actually we did earlier. Turbulent flow, we got 5.31 PSI. We call up the manufacturer and say, can you get us a 5.31 PSI pump? And they say, look, give me the feet head and I'll get it for you. So let's get that number up there. So I'm going to take 5.31. I'm going to multiply it by 144. And why am I doing that? That's to convert it for pounds per feet squared. Okay, and then I'm going to multiply, I'm in the denominator, I'm going to do the density of water. The 60-degree water is 1.94. Okay, and then I'm going to multiply it by 32.2, and that's feet per second squared. And then the units, if you're careful with it, will all work out, and that's going to end up being feet per water. Let me try that on my calculator. Oh, no. Okay, I'm getting a lot of feet of water. Let me check it a different way really quickly and see, make sure I get something up there that's reasonable. Okay, I'm getting about 12.2 feet of H2O. And that's going to be pretty significant. You could go online right now and look it up. Say, hey, give me a 10.65 GPM pump that can do 12.2 feet of head. What kind of horsepower is that going to be? Okay, last 2 columns to go. What if the flow was basically inviscid? Our situation was such that viscosity didn't really end up mattering all that much. Okay, well, what is the pressure drop? It's 0. Okay, there are no frictional effects, so there's no pressure drop. And what is the equivalent pressure drop in feet head? It is 0. Okay, well, look, you guys, that's it for this lecture. I need to give you some more details about what's going on. I don't mean to use the sort of like some of my family situation as an excuse, but really what I'm trying to do now is do the basics to get you guys keep moving forward. I will try before the end of the day to send you out an email talking about what's happening over the last little bit of the semester. Take care, be healthy, and get going on homework number 8. Seems long, but a lot of those problems are really short. I'll talk soon.